Hello everyone, welcome to the session on the YoloX Paper. This paper, entitled Exceeding YOLO Series in 2021, is by Zheng Jie, Zhongtao Liu, Feng Wang, Zeming Li, and Jian Sun of MacV Technology. In this paper, they explain how to switch the YOLO detector to an anchor-free manner and conduct other advanced detection techniques, that is, a decoupled head and a leading level assignment strategy, SIM OTA, to achieve state-of-the-art results across a large scale range of models. For YOLO Nano with only 0.91 million parameters and 1.08 gigaflops, the others obtain 25.3% average precision on the COCO dataset, surpassing a similar type of model, which is the Nano Det, by 1.8% average precision. For YOLO version 3, one of the most widely used detectors in this industry, it has been boosted up to 47.3% average precision on the COCO dataset, outperforming the current best practice by 3% average precision. While for a larger model like the YOLO XL with roughly the same amount of parameters as YOLO version 4 CSP and YOLO version 5L, an achievement of 50% average precision on the COCO dataset at a speed of 68.9 frames per second on Tesla V100 is gotten, exceeding the YOLO version 5L by 1.8% average precision. Models in the YOLO series have always been built with the idea of getting optimal speed and accuracy trade-off for real-time applications. To better understand this YoloX paper, let's take some steps back to the original YOLO paper, which is a YOLO version 1 paper. Now, the state of art at the time entailed going through several complex pipelines, and so with the coming up of this YOLO model, we were able to build an object detection system which doesn't rely so much on these complex pipelines, and hence could be used in real-life applications, since this is a relatively faster model as we look through an image only once. Let's understand how this is done. We have this architecture from the YOLO version 1 paper with a feature extraction unit and a classifier unit. Once an input is resized and passed in with a shape 48 by 48 by 3 as a typical image input, we get this output right here, and this output here is gotten from reshaping the output of the fully connected layer here. To get a clearer understanding of why we have this three-dimensional tensor as this output, we have to go back to understanding the task we're solving. Now recall that when you have this type of image, the aim is to correctly locate that there is a dog and a bicycle, or dog, bicycle, and a car in this image, and correctly get their position. So we want to have a bounding box surrounding this dog and another bounding box surrounding this bicycle. This problem can be split into three sub-problems. The first one is that of classification. So we want to be able to say that there is a dog, bicycle, and car in this image. The next one is the localization. We want to correctly localize all these objects in the image. And then the third one is to say whether there is an object at a given position. Now all these three go hand in hand. Let's start with the objectness. As you could see, this image has been split into several smaller boxes. In this case, or in the example from the paper, it's forms now a 7 by 7 grid. See 1, 2, 3, 4, 5, 6, 7, and then 7 this way. So we've split up this image into this 7 by 7 grid. For each grid, let's take this one as an example. We're going to say whether there is an object or not. So when creating our data set, we're going to have a 0 right here because there is no object related to this grid right here. The only object could have been this, but in this case you see that there is no object right here, except that you're maybe detecting trees. In that case you would want to take this as an object. But for this case, we are working with popular data sets like the Pascal VOC and the COCO data sets, which don't take trees into consideration. Now we move to the next. So we've said that in this cell right here we have no object. For the next 4, given that we have no object, we are not going to take all of them into consideration, same as all the rest. So we're not going to be localizing any object, so we don't have to take this into consideration. And then we're not going to be classifying any object in here, so all this will not be taken into consideration. Now let's suppose, or let's shift this to a position somewhere around, let's say this position right here. You see that this happens to fall at the center of this dog right here, and this means that we're gonna have this object next call to be equal 1. Now you could see you have times the IOU. The reason why we have this is because when doing training we have the ground truth, which in this case, for example, is 1 for this case, for this cell right here, and then we also have the predicted value. And the way we want to work this out is, if we have this cell here which predicts a value greater than say 0.5, or which predicts a value, and then we want to make sure that the box which has been predicted is as close as possible to the actual ground truth box. And to measure that closeness, we use what we call the IOU score. So we have to multiply that prediction by the IOU score to say whether there's actually an object here or not. Now this will go a long way to avoid us from having situations where the model predicts boxes which are not very close to the ground truth boxes, or whose dimensions aren't similar to that of the ground truth boxes. Then continue with the cell right here. We would also have this 4 different positions. You see you have the X, Y, W, H values, which would permit us draw out a bounding box around this or surrounding this object. And then finally we have this classifier outputs, where we will have all zeros except a 1 for the position where we have a dog. So we want to put a 1 where to say that there is a dog, and then the rest of the other classes will take a value of 0. And see clearly how we are able to come up, or how we work with these types of outputs. With the YOLO loss, the model is now trained end to end without any complex pipeline, since all we have to do is to pass in the image, obtain the output, compare it with the ground truth outputs, and then continue training until we attain convergence. Fast forward, we move to the YOLO version 3, where there were 2 major additions, or 2 major improvements to the original YOLO version 1 and even the YOLO version 2, which we'll not discuss here. We have the usage of anchor boxes and predictions across different scales. To understand the reason that for the predictions across different scales, let's take this input image right here. As you could see, some of those objects are quite small compared to the others, and so using the same grid size in detecting the bigger objects and the smaller objects isn't a great idea. So why not have, say, 3 different outputs where each output has a different grid size and is specialized on a given type of object based on its size. The YOLO version 3 model looks like this. Here we'll replace it with a darknet model, and so we would have the 3 different predictions. So we have the 7x7, we have the 14x14, and we have the 28x28. So here's grid size 28, here 14, and here 7. For the anchor boxes, the idea is why try to predict this ground truth anchor, or rather ground truth bounding box right here, when we could predict this bounding box from a set of pre-computed boxes known as the anchor boxes. And so if we take this example where we have this aeroplane right here, we have this 4 pre-computed anchor boxes. You see that this very last one right here would permit us easily predict this right anchor box, since it's already very similar to this ground truth. And the way this pre-computed anchor boxes are chosen is by an initial study of the data set you're working with, to make sure that you're picking up or you're working with pre-computed bounding boxes or anchor boxes which look very similar to the ground truth boxes. Now that we understand the context, let's get back to the YoloX paper. As we had seen, the Yolo version 3 uses anchor boxes right up to even the Yolo version 5. But nonetheless, over the past 2 years, major advances in object detection, academia have focused on anchor-free detectors, that is, working with no anchor boxes, and advanced label assignment strategies with end-to-end non-max suppression-free detectors. To better understand the concept of the non-max suppression, let's look at this figure from the Yolo version 1 paper. We suppose we have this image which is passed into the model, and then we have all these predictions right here. Now the boldness or the thickness of each line represents its objectness probability score. So the thicker the line, the higher the probability that we have an object. That said, many times we may have situations where one object has been predicted with so many bounding boxes, and so to take off the other bounding boxes, what we use is the non-max suppression algorithm. As the word goes, we have non-max, meaning we are going to take off all the other bounding boxes which are very similar to a given maximum bounding box. Like, let's say in the example of the bicycle, we have this bold bounding box right here, and by maximum bounding box we simply mean a bounding box where the objectness score is the highest compared to the other surrounding bounding boxes. So here we take off the other bounding boxes, and then here's what we're left with. Nonetheless, the idea of the YoloX or the YoloX model comes into avoid this situation right here where we have so many predictions for the same object. So we just want a non-max suppression free algorithm where we have predictions which leave from the input, or we have predictions from the model which go directly and get this. So we leave from the input and then directly here's what we get. We don't have to pass through this non-max suppression phase. An important point to note is that the others don't use the Yolo version 4 and Yolo version 5 as a baseline, but they instead use a Yolo version 3 as a starting point, and more precisely the Yolo version 3 with a darknet 53. Now what's going to follow next is a series of improvements which were made on this base model, and it's all those improvements which make up the YoloX model. So right here we have some implementation details. We have the model's been trained for over 300 epochs with 5 epochs warm up on the COCO dataset. They use linear scaling where the learning rate is a function of, or it's a linear function of the byte size. There's an initial learning rate of 0.01 and cosine learning rate scheduling is used. The weight decay is 0.005 for regularization, and momentum for the stochastic gradient descent is 0.9. Byte size 128 by default to typical 8 GPU devices. The input size is evenly drawn from 448 to 832 with 32 strides. That's it for the implementation details. We move to the Yolo version 3 baseline. This baseline adopts the architecture of the DACnet 53 backbone and an SPP layer, which is in the Yolo version 4 paper. They also add the exponential moving average weight updating, cosine learning rate scheduling, IOU loss, and IOU aware branch. And then they use the binary cross entropy loss for training classification and objectness branch, and IOU loss for the localization branch. Now, in previous Yolo models, for this classification block right here, we would use a categorical cross entropy loss, since we have, say, n number of classes, and then when our model predicts a given class, we train our model to do classifications correctly using that categorical cross entropy loss. But now we see that instead of the categorical cross entropy loss, we're using a binary cross entropy loss, meaning that for each and every position we have in this list of classes, let's suppose we were working with a COCO data set with 80 classes, for each one of those 80 positions, a binary cross entropy error will be computed for a corresponding or for the corresponding position in the ground truth level. The same will be done for this objectness score right here. So once we predict the objectness score, we are going to use the binary cross entropy loss just the same way we did even with the Yolo version 3. Going into the localization, instead of using the regression loss which we had in the Yolo version 3, here we're going to use the IOU loss. Here's what that regression loss looked like. It was basically comparing the X, Y, W, and H ground truth values with the predicted values. And then here we had to subtract it and square it and then sum. So it's a sum of the square of those differences. While for the width and the height, we actually use the square roots of the widths and the height. In order to understand the IOU loss, let's get back to the IOU loss paper. You see right here, those two boxes whose IOU has been computed. Note that IOU stands for intersection over union, also known as the Jacquard index, and its value tells us how similar two boxes are. When two boxes fit in perfectly, like say these two boxes, we have this light orange and then this orange. So when these two fit in perfectly, the IOU value is equal 1, but when they don't meet, the IOU value is equal 0. And so this IOU value or score takes number values between 0 and 1. Now, the way we compute the IOU score is by finding the intersection or the area of the intersection between the two boxes. That is this area right here. You see, take this, here is it, and then dividing it with the union of the two. So if we find the union of this two, we would have this. So we now take this intersection and then divide with the union. Obtaining the union simply means summing up these two areas and then subtracting the intersection to avoid counting the intersection twice. That said, every time we have a prediction for the localization, that's the X, Y, W, H predictions, we come up with this bounding box and then compare that bounding box with a ground truth bounding box. And the way that comparison is done is by obtaining this IOU score. We see here we have the computation of the area and the computation of the, or rather the computation of the intersection and the computation of the union to obtain the IOU score. And once that is obtained, we have now the IOU loss, which is equals 1 minus the IOU score. And the reason why we do this is simply because we're trying to maximize the IOU score. And so since we want a loss function where we're trying to minimize its value, we take 1 minus the IOU score, such that now we are trying to minimize 1 minus the IOU score. Coming back to the paper, the authors also conduct random horizontal flip, that's for data augmentation, random horizontal flip, color jitter, and model scale for data augmentation, as we earlier mentioned. What's also important to note here is that discard the random resize crop strategy, which is used in previous YOLO versions, because they found out that this overlapped with the mosaic or the planned mosaic augmentation strategy, which is to be used. With this enhancement, the baseline achieves 38.5 average precision on the COCO validation dataset. We then move to the next improvement, which is that of the decoupled head. Before looking at the decoupled head, let's first start by understanding this coupled head, which was used in the YOLO version 3 to YOLO version 5 models right here. By heads, we mean there's different output predictions at different scale. With a coupled head, with each or for each scale, we have this output right here, height by width by the number of classes times the number of anchor boxes plus the 4 different bounding box values times the number of anchor boxes times the object score times the number of anchor boxes. The problem with this way of representing this output is that generally we have this classification and this localization tasks which compete with each other, as the model is struggling to at the same time correctly classify and also correctly localize each and every object. Because of this problem, the decoupled head is being used in the YoloX model, where once we have this input head right here, it has been split up into 2 main sections. Here we have 2 3x3 conv layers, as we have here. So here we have 2 3x3 conv layers, which provides an output, and then that's what's used as for classification. And then for this other split, the output we have from here is again further split, such that we have this output for the localization and then this output prediction for the objectness. It should be noted that this decoupled head permits the model to converge faster, as you could see right here in this figure 3. We have this plot right here showing how the decoupled head permits our model converge faster compared to the coupled head. The next addition to the YOLO version 3 baseline is strong data augmentation. Here the authors add mosaic and mix up into the augmentation strategy to boost YoloX's performance. And by doing this, they found that pre-training the backbone on ImageNet is no more beneficial, and so they train the model from scratch. To better understand the mix-up augmentation, let's look at this paper entitled Bag of Freebies for Training Object Detection Neural Networks. We see here how these 2 images have been mixed up. So we have this image 1 and this image 2, we mix them up, and then we have this output image right here, with the bounding boxes still surrounding the objects. We have this top, we still have this bounding box, and then we have the sheep, this first sheep right here and this other sheep. Now generally in mix up, we attach a weight to each image just like this. So it's just like we have this image by a given weight plus the other image by a given weight to give the final output image. The next addition is that of an anchor free model. So in order to come up with a very fast model, the YoloX adopts this anchor free mechanism, which reduces the number of design parameters, since now we don't have to deal with the anchor boxes anymore. And so for each location, instead of predicting output for 3 different anchor boxes, now we just have only one prediction. And then the center location of each object is considered as the positive sample, and there's a predefined scale range. The next addition is the multi-positives. To stay consistent with the assigning rule of the YOLO version 3 model, the above anchor-free version selects only one positive sample for each object, meanwhile ignores other high-quality predictions. However, optimizing those high-quality predictions may also bring beneficial gradients, which may alleviate the extreme imbalance of positive-negative sampling during training. So yeah, they simply assign the center 3x3 area as positives, also named center sampling, as in the YoloX paper right here. This paper entitled Fully Convolutional One-Stage Object Detection makes use of center sampling, where we work with a set of samples which are around the center of the object and which have the best quality bounding boxes. This improves the performance of the detector to 45% average precision. The next modification is that of advanced label assignment. This is based on this paper by the same authors of the YoloX paper we're reviewing, entitled Optimal Transport Assignment for Object Detection, hence the name OTA for Optimal Transport Assignment. In this paper, the authors review the fixed label assignment techniques which have been used previously and some dynamic label assignment techniques, and now describe their own method which entails dynamically picking up the best or the top K best positive samples which can best represent a given object. And then finally, they add two additional kind of layers, one-to-one label assignments and stop gradient, which enable the detector to perform in an end-to-end manner, although this slightly decreases the performance and inference speed. Now, because of this extra efforts made to have an NMS free, that's non-max suppression free model, as we said previously, we have this drop in performance right here. Nonetheless, the best performing model, as we could see, is this one which takes into consideration all these additions. Right up to this, we have 47.3 average precision with a pretty fast model. Now, other backbones were used, that's besides the darknet 53, like this modified CSP-net backbone which was used in the YOLO version 5, and explain that the reason why the do or carry out experiments with this is for comparison purposes, since YOLO version 5's backbone is a modified CSP-net. From this, apart from this type of backbones, we have the backbones for the tiny and nano detectors. Now, obviously, this is clear because depending on the kind of device on which you want to deploy your model, you want to have a reasonable speed. Now, apart from this, it's important to note that the data augmentation strategy varies with the model size, as they explain that certain data augmentation strategies work best only for larger models, while others work or perform best for smaller models. Now we could compare the YoloX models with the state-of-the-art models, or better still, the state-of-the-art Yolo models. We have the YoloX L right here, YOLO version 5L, YoloX darknet, YOLO version 5 darknet, efficient net. So we see clearly that the YoloX performs better and faster than its YOLO version 5 counterparts. And this is the same for the smaller models. On this table 6, we have a summary of all those comparisons You'll see clearly from here that our best average precision is gotten with this YoloX model right here, which uses this modified CSP.NET model that's also used in the Yolo version 5 model. In conclusion, the authors present some experience updates to the Yolo series, which forms a high-performance anchor-free detector called YoloX, equipped with some recent advanced detection techniques, that's the decoupled head, which we've seen, anchor-free and advanced labeling assigning strategy. This makes the YoloX achieve a better trade-off between speed and accuracy as compared to its counterparts. And the authors also make available this code right here where you could build object detection projects now very easily based on your YoloX code, and then export your model in different format. Thanks for watching. See you in the next section where we are gonna train our YoloX model on our custom data set.